This video is sponsored by Brilliant.
I love Onshape. I think it's great CAD modeling software. But we all know that CAD, creating a part or an assembly, is not the end-all be-all. Eventually, you have to test that part to make sure that it's going to work in real life. Will it bend? Will it break? How much load can it take? How much thermal can it take? What are the parameters that we have to test for when creating a part? Luckily, there's simulation to do that. We're going to look at 3 different softwares that we can use to do simulations in Onshape. All 3 of these are completely free to use, at least for a trial. We'll be using this plastic bracket from that homemade robotic arm as the example. It's made out of PETG plastic, which bends, warps, and vibrates during operation. We'll start by using this simulation software called SimScale, and I'll click on Create Project. We can select a model right from Onshape, and we're going to select Status, Structural Simulation. We're going to click on Create Simulation. We're going to select for the material PET, P-E-T, and we're going to hit Apply. And now for our boundary condition, we're going to click on Fix Support. We're going to select this bottom face. We could hit OK. With that selected, we just have to add a force. I'm going to select where I want the force to come from, these faces, and you can see that the arrow is actually pointing in a direction that the force will be applied. And now we could see the fruits of our labor, the results of the simulation. Simulating the strength of this bracket is not going to tell us the whole story. What we really want to know is how it'll deal with vibration when it's actually in use. Here's a motor assembly that bracket attaches to. As you could see, this DC motor rotates at a certain RPM. We can use that RPM to figure out the frequency of the motor and how it's going to affect the bracket in an assembly. This time we'll try CAEPlex to do a modal analysis, and we'll set the motor frequency to about 100 Hz. Here's where things get wacky. We can over-exaggerate that vibration through the bracket to have a better understanding of what's going to happen when it's actually in use. We could change the angle of how that force is going to be applied, and we can see all of the different ways that it's going to be affected. Let's assume that our motor vibrates at about 100 Hz. That means that this bracket, which also vibrates at about 100 Hz, is a terrible option because it's going to vibrate at its most when the motor is rotating. So we're going to have to change the material. This bracket is made of nylon 6. It vibrates at about 130 Hz, so a little bit different than the motor, but even though this is much stiffer and better, it still is having some issues in simulation. So we're gonna have to bring out the big guns. This bracket is machined out of aluminum. It has a frequency of about 400 Hz, which is very different than the motor frequency. So we're not gonna experience a lot of the same issues with this bracket. Here's a final test of the robot, and you'll notice that the aluminum bracket makes it shake a lot less. Being able to simulate the bracket is pretty helpful, but how can we simulate the entire robot arm all at once? Luckily, there's this new software called ProtoTwin. Out of all the simulation softwares that we've looked at, this is definitely the most exciting to me. As amazing as this software is, it's still very new, and there's very little documentation so far on how to use it to control robotic arms and robotic systems. That being said, I want to show you a simple example using this system, and we'll see how we can change the sensors using this block-based coding language. This conveyor belt for boxes uses 2 laser beams to detect the presence of a box. If the beam is broken, it will show a false value on the right-hand side and will turn off the conveyor temporarily. We can use the block-based coding software, SoftPLC, which is included, to change the number of boxes allowed, resulting ultimately in a huge mess. Let's see how that plays out over time. We can also increase the speed of the simulation to show a much faster degradation of boxes. Speaking of visual feedback, I'm a visual learner. That's why I love using Brilliant to learn new skills in engineering, science, and math. Brilliant has thousands of interactive lessons that help you get smarter day by day. A few of the things that I like about it is that the lessons start at the basic level and then gradually become more and more difficult, covering more and more complex topics. I'm also a big fan of the fact that they have a mobile app. It allows you to learn the same things that you can on your laptop on your phone when you're on the go. Spending just 15 minutes to a half hour during my lunch break looking over these advanced topics really adds up over the weeks and months to follow. You can try Brilliant for 30 days free using my sign-up link. You can also get a 20% discount on a yearly subscription if you feel you really like it. Now back to the video.
Let's look at another example with this gantry robot that moves boxes from one conveyor belt to the next. Just as with the other example, we can turn off that sensor and let all the boxes fall off the end of the conveyor belt. But I could also program it so that that sensor works, and every time a box hits it, it automatically stops. But if I were to move the box manually, then the conveyor belt would continue moving. How do we make a surface into a conveyor belt? We just have to select it as a transport surface, and then choose a direction of travel, and then select the belt as a motor. And it's that simple. To turn the geometry of the beam into a sensor, all we have to do is select it from a drop-down, and it will automatically detect when it's broken by another object. That object will come up in the object menu every time it breaks the beam. We can also select the beam as a distance sensor. This is useful because now we can detect the height of objects moving along the conveyor belt, and the robotic arm can filter out which objects it wants to actually pick up. Being able to see these changes visually is very useful. The robot knows which objects to pick up and which ones to filter out. There are also position sensors, orientation sensors, linear angle, and accelerometer sensors as well. This programming of sensors is common in all of the machines that we can control using ProtoTwin. It seems like this whole software package is all based on being able to control mechanical systems using all sorts of different sensors, and then using TypeScript programming to create complex relationships between those sensors and motors. All of the things that I'm showing you on screen, all of these fancy assemblies, are just examples that ProtoTwin offers you to look at. You can't really modify them. This software is a little bit too new for me to be reviewing, so I can't wait to see what they do in the future and what I could use the software for. Thanks for watching.